Raghavan at one point found that he could not make enough money doing molecular modeling. So he said one day Biosim made him an offer, which was doubling his salary at that time as a postdoc in NIH Bethesda. So he went to Biosim. Biosim company was taken over and it has gone through various corporate takeovers and mergers. Today, last I knew, this is called Axelris. A company called Axelris today owes its origin to Biosim. And I learned from Professor Bayer that Hegler could not get a job in Weizmann. He decided to go back to the United States and form this company. I suppose he must have made a good amount of money. Now this is the article that I referred to. Levitt gives many things, whatever I have told you, right? Much of it comes from my portion about Karplus. Karplus Porter Sharma, that part of the story I knew from my thesis supervisor and from the literature. But the rest of the story is told by Levitt in his article Nature Structural Biology in 2001. Now here is the diatomic potential, here is the harmonic oscillator potential that is normally C, where you F equal to minus kx and V equal to half kx, right? So you have a parabolic potential. So if a molecule undergoes stretching motion, you do half kx. X is the displacement from the equilibrium geometry. That is a linear displacement. But you can have angular displacement. In the case of angular displacement, you can do either in terms of a theta or in terms of a sine theta. For small displacement, theta is equal to sine theta. So you can do the same thing, half k theta, theta minus theta 0 square. For example, carbon dioxide equilibrium geometry, theta 0 is 180. So you take a displacement. So you essentially have a harmonic oscillator potential. Here in this case, it is the bending motion. Now if you remember, Lifson wrote his paper about organic molecules, small organic molecules. Ethane is a good example. So in ethane, the bending motion of H with respect to the CC bond here gives you the theta, that gives you the displacement. Then you can have a torsional angle. The ethylene molecule that you look at in terms of a staggered configuration to eclipse configuration. So you go from eclipse configuration where the two CHs are like this to a staggered configuration where they are not eclipsing each other. So that is a displacement. So that is a dihedral angle you have, the conformational change that you have. There you use a slightly different one. You have 1 minus cos theta. Of course, 1 minus cos square theta will be equal to sin square theta. But instead of that, you just have a linear function in terms of cos cosine here. And for every, as the molecule gets larger, now you quickly graduate from ethane to a protein, a peptide, a polypeptide, and you go to a protein. Now every molecule every atom is going to be bonded to a nearby atoms. But every atom is going to have a long range interaction with another atom present in the same molecule. So this long range interaction is given by your standard Lennard-Jones potential. At that time, people are quite happy with the Lennard-Jones potential. This is what is called a non-bonding interaction. This is a displacement from an equilibrium geometry, and this gives displacement for bonded species. This gives you short range repulsion and a long range attraction. So that is Lennard-Jones potential, and there could be sometimes positive charge if you have a Zwitter ion, like glycine, the amino acids exist as Zwitter ions. The protein molecule, one end is positive, other end is negative. So you will have electrostatic attraction. You just simply use the Coulombic potential, and of course you can introduce a factor here to adjust for the interaction arising from solvation, etc. So this has all the elements that you require to study the molecular mechanics of a polyatomic molecule. Only thing was, so the basic machinery is here. Now you build as big a molecule as you want. This is where you decide what kind of a computer you have, what kind of a system that you can study, what kind of a questions that you can ask. In the 70s and 80s, we learned, we're excited about looking at what you normally take today in terms of computer screen was a big deal in the 70s and 80s. 80s and 90s, silicon graphics was a big deal. So you would like to see the atoms, you would like to see the molecules bend and twist and variety of motions, and you could see. And protein folding takes you on a much another orders of magnitude more complicated problem. You go from ethane to propane to butane to etc. You have an alkyl chain. As the alkyl chain gets longer and longer, number of conformational possibilities increases. But in a protein, they like to twist. You have a helical twist. They like to bend. You have a beta vector, and there are the other aspects of the molecule. We have a very complicated. We had a symposium about 3 weeks ago on ubiquity. A large number of atoms are present, and they are all bond. Many of them are bonded to each other. There is a bonding interaction, non-bonding interaction. Now, to see how a molecule, a large protein molecule, reaches its native state, which occurs in nature, there is what is called Eisenthal paradox. If you take one methyl group, another methylene group, etc., if you go systematically one by one, it will take forever, millions and millions of years. But nature, within a cell, is able to put amino acids together and produce proteins in its natural state, or what is called the native state. So this problem has remained. So people have all kinds of theories. Now the molecular motion, when a bond breaks and forms, it is of the order of 10 to the power minus 15 seconds. A few hundred, well, a couple of hundred femtoseconds. This was known from theoretical modeling. Of course, when Weil was able to demonstrate in the laboratory and say you can watch molecules, bonds form and break, he got a Nobel Prize. People knew the atomic dimensions of the order of angstroms, and then of course subsequently he wrote papers where you try to watch a molecule undergo photodissociation in real time using electron diffraction and some tools. Now this is how much we are able to look at small molecules. You do the same thing with larger molecules. You see them bend, twist, etc. And the enzymes, they have very important role to play as a biological catalyst. We have to model each one of them. So the problem gets more complicated. And of course, depending upon the problem of interest to you, you are going to adopt a particular approach. So what these three people did, of course, for these three people, probably there are 300 other people who were contributing. Their group, Allinger's group, used to do a lot of these molecular conformations using models. So these physical models that were transformed into computer doable model problems. So this is where the transformation took place from modelistic models which you have to computer models. Scaling up is no longer an issue. Now the reason I mentioned about femtosecond is that is the time scale in which bonds break and form. Then you have a picosecond, rotational motion takes place. Then you have a nanoseconds, microseconds, milliseconds, and of course you and I live for years. As you scale up in time, you also scale up in space. These models have to undergo a different, what you call a paradigm shift. You have to go beyond them. You have to treat groups of molecules or a group of atoms as a larger entity, what is called a coarse-grained model. You switch from a femtosecond time scale to several seconds and years. You go from angstroms to centimeters and meters. So there is a multi-scale modeling involved. So today, it's the right thing to do to work with the multi-scale modeling to do this patchwork or whatever you want to call it to solve larger practical problems. So here is the summary. This is a reproduction from Levitt's article in Nature. I skipped the first one because it refers to somebody else who was working in structural biology, starts with reference number 2. You can see Lipson was publishing in tetrahedron, Lipson and Warshall published in Chem. Levitt and Lipson start published in Journal of Molecular Biology, and then there is Levitt in Nature. Levitt, here is a PhD thesis on conformational analysis, and you go to the next one. So Levitt in polymerization in biological systems, Levitt and Warshall in Nature. So by that time Warshall has come back, then Warshall and Levitt, and then Warshall in Nature, Levitt and so on. And then he has other papers, and then there is a complex. And Andy McCommon, before coming here, where they were talking about Andy McCommon, he tells me that he say whatever he would like to say. So this is how the field has progressed as a said, the basic tenets of whatever was required was built in those models. And of course, today, these three people are famous people. For about a year or so, until the 2014 Nobel Prize was announced, these are the stars. And this gives you an idea, a little bit of background into what they were and how the field developed in practice.
Good evening. I will just add a few things because I guess Professor Sathyamurthy said I was a contemporary of some of the people there in the Weizmann Institute. This was in the 60s. I must admit that I don't know so good or hardly know Mike Levitt. He was those days he came to the Weizmann Institute. The way that it was described by Professor Sathyamurthy was sent by the English to learn some of the techniques that were developed actually by Schneur Lifson. As far as Schneur Lifson is concerned, he was working together in a group with the Katzir brothers. You know, there was Aaron Katzir and Ephraim Katzir. And those were famous I believe it was biologists or maybe chemical biologists and physical biologists. The more prominent one was Aaron Katzir from the two brothers, and he was murdered during an attack by a Red Brigade person from Japan in the airport of Tel Aviv. That was, I believe, in '75 or so. It happened. He was just this guy, was one person who came in with a machine gun and killed 30 people there at the airport. And among them was Professor Katzir, who was really the head of this group. Ephraim Katzir, his brother, became later the president of Israel. So this was essentially the background for this. I believe some of those models are also associated with these two people. I think Ephraim Katzir, I believe, still lives. No? I think he still lives. They were all in the Weizmann Institute. Schneur, a very funny guy, very easygoing person, very friendly. Was the head of the chemical physics department, the Weizmann Institute. There was very few people there. We have a common friend called Rafi Levine. Rafi Levine was invited by Schneur Lifson actually to join the department to create a group of dynamicist people. And I was also in this framework. I was asked to join the Weizmann Institute, at least as a part-time, because I was associated with the nuclear reactor in Sorek. So that's how I got into the Weizmann Institute for about 10 years or so. But for some reason, the physicists didn't like this book. The physicists decided that what these people are doing is not important. And that's essentially the main reason why some people didn't get their permanent position there. Warshak was rejected. Arnie Hagler was mentioned here. He was there. It's luckily enough that Ada Yonat somehow made it. You know, Ada Yonat is another person that got the Nobel Prize because she was not doing too much things that the physicists understood. They thought that they understood what Lifson is doing. Actually, I'm not sure how much they appreciated Lifson himself. So that was another thing. We are talking about people like Talmi, Talmi and Amos Deschalit. Maybe some of you heard of them. Of course, the audience here is not physicists, but the physicists. Those are essentially nuclear physicists. Pardon?
There are some physicists sitting.
There are some physicists in the audience. So sometimes those physicists can do really a lot of harm. So that's So Marshall came in. Marshall came from the Technion. He was doing his, he did his bachelor degree at the Technion with pounds. Not with pounds, you don't do it with pounds, but it was still a bachelor. But maybe he did a master with pounds, Professor Pounds from the Technion. I think maybe you heard about him. So he came there to work with Schnell. Now, why would he come work with Schnell? I think the motivation was the computer. There were two centers of computers in Israel in those days. We are talking about the 50s and the 60s. One was with the army, of course. That's where I learned how to work with computers. This was in 61. I took the course in Fortran. Actually, it was not in Fortran, it was in Alta, but that's a different story. Then I went to work. I did my PhD at the Weizmann Institute, and as Professor Sathyamurthy mentioned right now, the first paper, I'm not really a chemist, by the way. I'm not a chemist at all. I'm not a chemist at all. I never took a course in chemistry. But I was offered by a person who was working at the Soviet Nuclear Research Center to do my PhD in dynamics, in molecular dynamics. And he told me, this guy, by the way, Professor Sathyamurthy, I don't think you know his name. He was more involved in hot atom chemistry in those days. We are talking about the middle of the 60s. And so he told me, I was at a conference in the United States, and then suddenly I saw a guy getting up and giving a talk about those trajectories, classical trajectories to do chemical reactions, and so forth. It sounds to me very